Welcome, everyone. I'm excited to introduce today's presentation on essential concepts for understanding optimization problems with linear constraints. The focus is on definitions in linear programming. During this session, we'll explore the key ideas that form the foundation of linear programming, helping you grasp how to approach and solve these types of problems efficiently. Let's get started. Let's talk about what a linear programming problem really is. Essentially, it's an optimization challenge where the goal is to either maximize or minimize a specific objective function. Now, this function is linear, meaning it has a straight line relationship, which makes it easier to analyze and solve. But of course, we can't just focus on the objective alone. There are constraints, conditions that the solution must satisfy. These constraints are also linear, which keeps everything consistent and manageable. Usually, these involve non-negativity restrictions on the decision variables, meaning the variables can't be negative. They have to be 0 or positive. This setup is fundamental because it reflects many real-world situations, like maximizing profits or minimizing costs, within practical limits. Understanding this structure helps us see how linear programming provides a powerful framework for making optimal decisions efficiently. Let's take a closer look at the components of the objective function. Here, the variables x1, x2, all the way through, represent our decision variables. These are the choices or actions we can control within the problem. Correspondingly, the constants c1, c2, up to are the coefficients, or parameters, that weigh each decision variable's contribution to the overall objective. The goal is to maximize or minimize a linear expression, which we call z. This z is essentially a sum of each decision variable multiplied by its respective constant, like c1 times x1, c2 times x2, and so on, all the way to cn times. This form is quite flexible because it can model different goals, whether we want to maximize profit or minimize costs, time, or other resources. The key idea here is that the objective function provides a clear, mathematical way to quantify what we want to achieve, guiding us toward the best decision variables to meet our goal. So, in essence, the objective function is the heart of our optimization problem. It captures exactly what we want to optimize, expressed in a straightforward linear form that makes it easier to analyze and solve. Now, let's talk about equality or inequality in the context of linear constraints. As you can see, we can use the symbols less than or equal to, or greater than or equal to, depending on the specific restriction. The key expression involves a sum, ai1 times x1 plus ai2 times x2, all the way up to an times, and this sum is constrained by one of those symbols, compared to. This form is what we call the general form of a linear constraint. It's important to remember that these constraints represent the restrictions or limitations on our decision variables. And crucially, they must be linear, which means no powers or products of variables, so no x1 squared, for example, or x1 times x2. This linearity ensures our models remain manageable and solvable efficiently. So, in essence, these constraints define the feasible region where our solution can lie, shaping the problem into a linear programming model. Recognizing and formulating these constraints correctly is fundamental to solving optimization problems effectively. Now, let's look at these non-negativity constraints. What we're seeing here is that each decision variable, x1, x2, all the way up to xn, must be greater than or equal to 0. This is a very common type of constraint in many real-world problems. For example, if you're deciding how many items to produce or how much resource to allocate, it doesn't make sense to have negative quantities. So these constraints ensure that our solutions stay realistic and feasible. They basically prevent us from considering impossible or nonsensical options, keeping our decision variables within a logical range. This is a fundamental concept that helps us define valid solutions in optimization problems. So let's talk about what it means for a solution to be feasible. Essentially, if we have a set of decision variables, which we can denote as x, that are made up of components like x1, x2, all the way up to xn, then this set is considered feasible if it satisfies every constraint in the problem. This means that each of those variables, when plugged into our constraints, doesn't violate any of the rules we've set. In other words, it fits within the boundaries defined by our problem. Now, when we verify whether a specific set of values is feasible, we're checking if it satisfies all these constraints, including the non-negativity restrictions, which are quite common in optimization problems. And this leads us to the formal definition of a feasible solution. It's simply any set of decision variable values that meets all the constraints of the problem. So, in summary, feasible solutions are the candidates that could potentially be optimal because they respect all the rules we've established. Now, let's talk about basic feasible solutions, or BFS, in the context of linear programming. When we have an LP with m independent equations and n variables, where is greater than or equal to m, a typical BFS will have at most m basic variables. The remaining variables, which are non-basic, are usually set to 0, and there can be up to n minus m of these non-basic variables. It's important to verify that the resulting solution is feasible, meaning all variables must be greater than or equal to 0. So, after selecting a set of basic variables, we set the remaining non-basic variables to 0, and then we check if the solution satisfies all the constraints. Before selecting variables, we need to convert the constraints into equations. We do this by adding slack or surplus variables, which transform inequalities into equalities, making it easier to work with the system. A basic feasible solution, then, is a feasible solution obtained specifically by choosing a set of basic variables and ensuring that all variables meet the non-negativity condition. This process is fundamental because it helps us identify the corner points, or vertices, of the feasible region, which are crucial in optimization. Overall, understanding how to verify feasibility and properly select variables is key to efficiently solving linear programming problems. Let's talk about the key idea here. If an optimal solution exists for a linear programming problem, then we can actually find it at a corner point, or what we call a basic feasible solution. This is a really important concept because it means that instead of checking all possible solutions, we only need to focus on these corner points to find our optimum. Now, whether we're maximizing or minimizing, this point at the corner gives us the best possible value of the objective function. For maximization problems, it provides the highest value of z, and for minimization problems, it gives us the lowest value of z. An optimal basic feasible solution, then, is simply the best basic feasible solution among all solutions that satisfy our constraints. It's the one that yields the most favorable value of our objective function, either maximum or minimum, depending on our goal. So, understanding this connection between basic feasible solutions and optimal solutions is fundamental because it streamlines the process of solving these problems efficiently. Instead of exploring an infinite set of solutions, we focus on these critical corner points to find our optimal value. Sometimes, during the simplex method, we might encounter issues like stalling, where there's no improvement in the objective value in some steps. However, it's important to remember that even if this happens, the solution can still be correct. Now, let's talk about the practical impact of this. Typically, a basic feasible solution, or BFS, involves m basic variables. If one of those basic variables is 0, then we say the BFS is degenerate. So, what's the difference between a normal BFS and a degenerate one? Well, a degenerate basic feasible solution is simply a BFS where one or more of the basic variables are equal to 0. This condition, having one or more basic variables at 0, is what we call degeneracy. It's an important concept because it can influence how the simplex algorithm proceeds and how we interpret the solutions. In summary, degeneracy can cause some complications, like stalling, but it doesn't mean the solution isn't valid. It's just a different scenario we need to be aware of when analyzing and solving linear programming problems. Now let's look at some important points to keep in mind. First, occurs when basic variables equal 0, may cause stalling. This situation is known as degeneracy and it can sometimes make the process of finding the optimal solution more complicated. Next, we have the concept that the best BFS, or basic feasible solution, gives us the maximum or minimum objective value. Essentially, this means that among all feasible solutions, the optimal one is the most desirable based on our goal. The optimum solution is typically found at a corner point, which is obtained by setting non-basic variables to 0. These corner points are critical because they often represent the best possible solutions within the feasible region. Speaking of feasible solutions, a basic feasible solution satisfies all constraints and has non-negativity. That means it fits within our problem's restrictions and doesn't violate any rules. Feasible solutions, in general, must satisfy all the linear equations or inequalities, which form the constraints of our problem. These restrictions are fundamental to defining the feasible region. The objective function is a linear expression that we aim to maximize or minimize. It's central to our problem because it guides us toward the best solution based on our criteria. Finally, to sum up the key takeaways, understanding degeneracy and corner points helps us navigate the solution space efficiently. Recognizing feasible solutions and the importance of the objective function keeps us focused on finding the optimal answer within the given constraints. All these concepts connect back to the overall theme of optimizing linear programming problems effectively.